So one thing I'm typically asked is, if the sun heats the ground, why is it cold at the top of the mountain, which is also ground? Well, that's what we're going to talk about with this lesson. And as you know, the sun heats the ground and the ground heats the air. But as you get farther away from that heat source, the temperature is going to cool off because the whole process is caused by conduction. The warm ground is touching the air, and that's what's warming our atmosphere. So in the troposphere, the level where we're at in our atmosphere, the farther you get from the ground, the colder the air gets. That's called a lapse rate. And we know specifically what the typical lapse rate of our troposphere is. It drops 6.5 degrees every 1,000 meters, or 3.6 degrees Fahrenheit every 1,000 feet. So on this diagram, there's our sun heating the ground and the ground heating the air. So if you have a big mountain, well, you're getting farther away from the heat source, which is the Earth. Let's say that mountain's 10,000 feet high. That's a drop of 36 degrees from the bottom of the mountain to the top. And an airplane flying overhead, they're typically at 30,000 feet to 35,000 feet. It's well over 100 degrees colder up there than on the ground. That's why it leaves that little contrail you see behind the jet. That hot air is coming out, much like your hot breath on a cold day, and it instantly condenses and forms ice crystals there that you can see. So I tried this out myself. I'm at the bottom of Mount Washington, New Hampshire here when I took this picture. The base is 2,000 feet above sea level. And at the bottom, I went to the ranger station and took a picture of the temperature, and it was right around 79, 80 degrees. Now the top of Mount Washington's at 8,000 some feet. It has a prominence of 6,100 feet. That's the height from the base of the mountain to the top. So if you do the math, so it's 6.1 thousand feet times 3.6 degrees every 1,000 feet. That's a 22 degree drop. So 79 degrees at the bottom minus 22 degrees equals about 57 degrees at the top. And not accounting for the time it takes me to drive to the top, these were the conditions on the summit of Mount Washington that day. And you can see 55 degrees, very close to where it should have been. The difference in temperature between the bottom and the top of Mount Washington is what kills a lot of people. They are dressed for summer weather at the bottom, then they hike to the top. They're not ready for the cold. Usually they run into some rain, and then the wind blows and evaporates the rain off their skin, so they get hypothermia. And lots of people have died trying to hike to the top of Mount Washington, even though there's plenty of signs that tell you, hey, make sure you dress in layers. In fact, when you get to the summit of Mount Washington, there's this plaque that I have a video of, and it shows you all the deaths that have taken place in the presidential range, of which Mount Washington's one of the mountains there. I know you can't read it, but every single little paragraph you see there is a person who died, the date, what they were doing, and what caused their death. It goes on to yet a second panel, and back when I was there, all the way back in 1998, there was a third panel starting. So if I go back today, I'm sure I'm going to see another whole panel added to the deaths on the presidential range. Mount Washington sticks up sometimes into the jet stream, which causes tremendous winds. This is a picture of the weather station at the top of the mountain. They actually have to use chains to hold it on. Now this is the old weather office on top of Mount Washington. There's a plaque on it that says the highest wind ever observed was recorded here in 1934. It was 231 miles an hour. Now, since that day, the record's been broken. It was broken by Tropical Cyclone Olivia off the coast of Australia in 1996. They recorded a confirmed 253 miles per hour. Mount Washington is manned all winter long, and with cold temperatures and wind adding to that cold, well, they get a little bit nutty. They recorded this video called The Breakfast of Champions, which imagines what it would be like to eat at an outdoor cafe on top of Mount Washington.
Not every moment is devoted to painstaking scientific inquiry. Witness Breakfast with a View, high above the presidential range.
That is milk instantly freezing as it comes out of the jug. Always wanted to know where that tablecloth ended up. More recently, in 2016, they recorded some people outside in the winds. They were able to actually sit into the wind. And it basically can lift them up if their body is the right shape. That's what 100-mile-an-hour sustained winds will do. So it's cold at the top of Mount Washington, and the wind just doesn't help at all. Very near the ground, the lapse rates vary greatly. It's not 3.6 degrees every 1,000 feet. We're talking about just the bottom 1, 2, 3 feet at the ground. It depends on the type of ground and the time of day that you're out there. So this is an example of what would happen in the mid-afternoon, where the ground heats up much quicker than the air does, just like the boiling water that I showed you in the last video. On this graph, you see that the red line is all the way over on the right, over 50 degrees C. And as you go up in altitude, it very quickly drops until it hits the lapse rate. Now at night, the opposite's going to happen. The ground's going to give off its heat very, very quickly, so it's actually going to be colder on the ground than it is in the air immediately above it. Again, the ground is going to cool quicker than the air. On a windy afternoon, the air is going to be mixed up pretty well, so it doesn't have a chance to stratify. And stratify means that hot or very cold air stays on the bottom and that milder or chillier air stays separated on top. On a windy afternoon, we're going to mix up the atmosphere very close to the ground, so we'll have a very stable drop in temperature, where if it's perfectly calm and the air doesn't mix that well, it can get very, very warm at the surface. At night, again, the opposite is true, where we're going to have a big change in temperature on a calm night compared to a windy night. So clear and calm conditions produce the biggest changes in temperature. And that's a big deal if you're a farmer, especially a citrus farmer down in Florida. If the temperature is going to get cold at night and the air's not going to mix, then you're going to get freezing on your citrus crops. So you burn these smudge pots to try to get some heat at the surface, or you set off windmills above your crop in order to try to mix the air and get the temperature to be more stable, because the last thing you want is for your oranges to freeze. Every winter there's some story about losing the citrus crop. As we head throughout the day, the swing in temperature is going to be more extreme. Once the sun first comes up, it's going to take a while for the ground to surpass the air in temperature, and it's not until we get to the mid-afternoon that the difference in temperature is going to be its greatest. Here's a video that explains it.
As the sun rises in the morning, the Earth's surface warms more quickly than does the air above. On a clear, calm day, the air in contact with the surface normally reaches its highest temperature at noon, when the sun's energy is most intense. However, the air several meters above the ground, where thermometers are usually located, typically reaches its highest temperature later in the afternoon. At night, the ground cools more quickly than the air. This situation causes the air in contact with the ground to become colder than the air several meters above, and a temperature inversion forms just above the Earth's surface.
So here's what we've learned from this lesson. The equinox is when the sun shines on the equator, and we have equal day and night, 12 hours in length, and the equator always has equal day and night. That's why it's called the equator. Solstice is when the sun shines on one of the tropics. The summer solstice, there's lots of sun for us in the northern hemisphere. That gives us our longest day on the summer solstice. It's not the hottest, though. That lags into July. The winter solstice, there's not a lot of sun for us because it's down in the southern hemisphere, and that causes it to be cold. That's our shortest day of the year. The sun heats the ground, and heat is measured with temperature. Temperature goes down in the troposphere at the lapse rate. And temperature is a physical property that describes the shaking of the motions of the air. So this is just one physical property we need to understand in order to predict the weather.